Alright, now let's delve into the world of the double-ended queue, also known as dequeue. A dequeue or double-ended queue is a special type of queue that allows us to insert and remove elements from both the front and rear sides. Unlike a regular queue that strictly follows the first in first out rule, FIFO rule, the dequeue provides us with more flexibility in managing our elements. Imagine a line of people waiting to enter a cinema hall. In a regular queue, the first person to arrive is the first one to enter the hall. But in a dequeue, people can enter or leave the line from both ends, giving us the freedom to handle the queue in different ways. Alright fellas, let's now explore the different types of dequeues. First, we have the input restricted dequeue. In this type of dequeue, we are limited to inserting elements at only one end. However, we can still remove elements from both ends of the dequeue. It's like having a line of people waiting to enter a bus and they can only enter from the front, but they can exit from both front and back. Next, we have the output restricted dequeue. This type of dequeue is the opposite. Here, we are limiting to removing elements from only one end, but we can insert elements at both ends of the dequeue. It's like having a line of people again, but this time they can enter from both the front and the back, but they can only leave from the front. So, you can see the dequeue offers us different ways to manage our elements, right? Depending on whether we want more flexibility in inserting or removing them. Understanding these different types of dequeues will help you to choose the right data structure for specific scenarios. Alright, now let's explore the circular array implementation of a dequeue. In this implementation, we use an array to create our dequeue, and if the array is full, we start inserting elements from the beginning again. This circular approach allows us to make the most out of available space. So, before we start performing the various operations, we need to take the following steps. First, we create an array, dequeue of a given size. So, let's call it n. Then, we set two pointers. One is called front and the other is called rear. Then, we initialize front to -1 and rear to 0. Alright guys, now let's learn about the insert at the front operation in our circular array based dequeue. When we insert an element at the front of our dequeue, we follow these steps. First, we check the position of the front pointer. If the value of front is less than 1, it means we have reached the beginning of the array. In this case, we reinitialize front to the last index of the array, which is n-1. If the value of front is not less than 1, we simply decrease the front pointer by 1, moving it one step towards the front of the array. Finally, we add the new elements, let's say it's 5, into the position pointed to by front pointer in the array. Great! Let's now explore the insert at the rear operation of our circular array based dequeue. When we insert an element at the rear of our dequeue, we follow these steps. First, we check if the array is full, which means there is no more space to add new elements. If the dequeue is full, we reinitialize the rear pointer to 0, starting from the beginning of the array. This is because we are implementing a circular array, so if the rear has reached the end of the array, we need to wrap it back to the beginning to make use of any available space. If the dequeue is not full and there is space for more elements, we simply increase the rear pointer by 1, moving it one step towards the rear of the array. Finally, we add the new element, let's say it's 5, into the position pointed by the rear pointer in the array. Let's explore the delete from the front operation of our circular array based dequeue. When we want to delete an element from the front of our dequeue, we need to follow these steps. First, we check if the dequeue is empty, which means there are no elements in the dequeue to delete. If the dequeue is empty, which means if the front pointer is -1, we cannot perform the deletion operation, and this condition is known as the underflow condition. If the dequeue has only one element, which means if the front and rear both pointers to the same element, we remove the element from the dequeue. So after deletion, we set both front and rear to -1, indicating that the dequeue is now empty because we have deleted the only element presented in the dequeue. If front is pointing to the last element in the array, which means front equals to n-1, where n is the size of the array, we cannot delete an element from the front as it will wrap around to the beginning of the circular array. To handle this situation, we set front to 0, going back to the front of the array. For all other cases, we simply move the front pointer one step ahead by increasing its value by 1. This action effectively deletes the element that was previously at the front of the dequeue. Let's delve into the delete from the rear operation of our circular array-based dequeue. When we want to delete an element from the rear of our dequeue, we need to follow these steps. First, we check if the dequeue is empty, which means there are no elements in the dequeue to delete. If the dequeue is empty, which means the front pointer is -1, we cannot perform the deletion operation, and this condition is known as the underflow condition. If the dequeue has only one element, which means front and rear both point to the same element, we remove that element from the dequeue. So after deletion, we set both front and rear to -1, indicating that the dequeue is now empty. If rear is pointing to the front of the array, which means rear equals to 0, we cannot delete an element from the rear as it will wrap around the end of the circular array. To handle this situation, we set rear to n-1 going to the end of the array. For all other cases, we simply move the rear pointer one step back by decreasing its value by 1. This action effectively deletes the element that was previously at the rear of the dequeue. Let's discuss the check empty operation of our circular array-based dequeue. The purpose of this operation is to check whether the dequeue is empty or not. We can achieve this by examining the value of the front pointer. So here is how the operation works. We check the value of the front pointer. If the value of front is -1, it indicates that the dequeue is empty because there are no elements in the dequeue. In other words, when front is -1, there is no front element, and hence there are no elements at all. Let's delve into the check full operation of our circular array-based dequeue. The purpose of this operation is to determine whether the dequeue is full or not. To achieve this, we need to examine the values of both the front and rear pointers. So here is how the operation works. We check the value of the front pointer and see if it is equal to 0. We also check the value of the rear pointer and see if it is equal to n-1, where n is the size of our circular array, or if front is exactly 1 less than rear. If either of these conditions is met, it indicates that the dequeue is full. Now, let's understand the two cases in which the dequeue can be full. The first case is if the front is at the beginning of the circular array, which means front equals to 0, and rear is at the last position, which means rear equals to n-1, it means our dequeue is full. The second case is if front is exactly 1 less than rear, which means front equals to rear plus 1, and it also indicates that the dequeue is full. The great thing about these operations is that they all have a constant time complexity denoted as big O of 1. So what does this mean actually? It means that the time taken to perform any of these operations does not depend on the size of the dequeue. Whether we have a small dequeue or a large one, the time it takes to insert, delete, or check whether it is full or empty remains constant. This is fantastic news because constant time complexity is very efficient and desirable in data structures. It allows us to handle our dequeue operations swiftly, making our code run smoothly and quickly, regardless of how many elements are in the dequeue. Let's now explore some of the practical applications of the dequeue data structure. Undo operations on software. So, have you ever made a mistake while typing or editing a document and wished you could simply undo the changes? Well, dequeue can be used to implement the undo functionality in software applications. So, it allows you to keep track of previous states or actions. So, if you make a mistake, you can easily go back to a previous version. Storing history in browsers. So, have you ever wondered how browsers keep track of the web pages you have visited? So, you can easily go back and forth between them. So, actually, they use the dequeue data structure to store these browsing data. So, when you click the back or forward button, the browser efficiently retrieves the previous or next URL from the dequeue, allowing you to navigate through your browsing history seamlessly. Implementing stacks and queues. A dequeue is quite versatile. It can be used to implement both stacks as well as queues. So, by using specific operations, you can transform a dequeue to either a stack, last in first out, or a dequeue, first in first out, making it a valuable tool in solving various programming problems.